In this lesson, we're going to cover domain. Domain are all the acceptable x values that we can plug into a function. For the most part, for a lot of the functions that we encounter, there are no restrictions. You can pretty much put in any number. Let's look at example 1. I'll first put a little title on this. This is all about domains. Okay, so those are going to be your possible x values. Let's look at this guy right here. Y equals 5x plus 2. Okay, so if we've got y equals 5x plus 2, if we draw this graph, goodness gracious, this is a lot more difficult on this. Let's see. We draw it like this. Y equals 5x plus 2, that's a line with a y-intercept of 2, a slope of 5, so it's not going to be perfectly accurate, but the line will extend all the way to the right and all the way to the left. It just keeps going forever. So the domain for this guy, all of our possible x values, since it'll continue on forever and ever, to the left will be from negative infinity to positive infinity. I use this as interval notation. The parentheses indicates that the number is not included in the set. You always use parentheses for domain. Or sorry, for negative infinity and positive infinity, because those aren't real numbers. So the next one, let's go to y equals 4x divided by x minus 3. Now, you are not allowed to divide by 0, ever. That's just one of the big no-nos. You can't do that in math. So if you're not allowed to divide by 0, that means that this value down here cannot equal 0. That means x cannot equal 3, because if x equals 3, 3 minus 3 would be 0, you'd be dividing by 0. So what's going to happen is that there will be an asymptote here, and you're going to have something that looks more along the lines of this. You'll have an asymptote right there. Actually, with this case, it would be a 1, 2, 3, 4 horizontal asymptote as well. I need some more space. It'd look like that. But the big idea, rather than going over these specifics, because I'm not doing a super accurate graph, I'm just giving you guys an idea, is that the domain will go from negative infinity. It'll keep going, keep going, keep going. There's this big problem here at 3. 3 will not be included. So we gotta remove the 3, and then from 3 to infinity, you've got a bunch of x values that you can use. You can use all of those values. Okay, that's the big deal with that one. So you can't divide by 0. That's one of the problems that we can't do. And that's one of the ways that we eliminate numbers from our domain. The next way will be having a negative under a root. Now, we can have a negative number under a root with imaginary numbers, but for real numbers, we're not allowed to have a negative under a root. So that means if I was to draw out this graph, and we'll talk about actually drawing out these graphs later, this guy will go to negative 2, and he'll kind of look like this. Again, not super accurate. But do you see how I can't go to the left? I can't go more than negative 2, because if I made this, say, negative 3 plus 2 is negative 1 under a root. I'm not allowed to have that. So for here, my domain is going to be from negative 2, and you see I use the bracket instead of the parentheses. The bracket just indicates that it's in the set, that it's included. Before I use the parentheses because I couldn't include 3. I couldn't include infinity because infinity is not a number. Here, negative 2 certainly works. I can plug him in, so he works. That's going to be a bracket, and that's going to continue on forever on to the right. That'll be the infinity. Okay, so Another example I'm not allowed to use by restricting domains is that I can't have a negative under a root. The last one that we're going to deal with is our logs. So a log, 1, 2, 3, 4, 5, 6, 7. This is going to be a log graph that's shifted over 7. I'm not allowed to have a 0 or a negative under a log, just because by nature what a log is it's giving the, you can think of this as b to the y equals this value. There's no number for x that I can plug in. I can't make this value here negative, that some y value as an exponent will make this negative. Exponents can't make a number negative, and they can't make a number 0. If y was 0, this should still be just, this whole value should be 1. So what happens here is the graph will look something like this. Obviously this has been shifted over, so this means that I can't have this value be 0 or negative, which means that from here with our root we were allowed to have a 0, so it was included, but here with this guy he will not be included, so I can't have 7. But I can have any value that's above that, because that'll just make that a positive inside. So that becomes that. So I can't have the inside of a log be 0, and I can't have it be negative. Okay. So those are some of the restrictions on domain, the numbers that I cannot have for x. The second part of this lesson is talking about plugging values in to a function. That just means that instead of having x, I'm going to substitute x with the number they're giving. So if right here f of x equals x squared minus 3x, f of negative 2 means I'm just going to plug in negative 2 for all of those values of x. You got to be careful with the notation, so this is going to be negative 2 squared minus 3 times negative 2. So negative 2 squared is going to equal 4, and then this guy is going to be positive 6, so that'll be 10. So that just means I plugged in the value here into there. And it'll get more complex when we have various functions that we're plugging into functions. This is just another way, example 6 is just another way of rewording it. They're saying if f of x equals blah 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 blah, name the ordered pair given by f of 4. An ordered pair just means that you're going to get an x comma y, right? So it means that when I plug in my x value of 4, what's the y value that comes out? So we just plug 4 into here and we get f of 4 equals 4 plus 3 divided by 4. 4 plus 3 is going to be 7 divided by 4. So that means that my ordered pair is going to be 4 comma 7 fourths. Okay, just plugging the number in. They also want you to be aware of intercepts. Where does f of x blah 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 cross the x-axis? Let's just look at this visually. If I have a number, this is x plus 7, so we're going to draw it like so. Kind of a rough graph. But the x-axis is this guy right here. Right, he's our horizontal axis. So what do we know about where he crosses the x-axis? Well, I know that my y value is 0. That's what I know about that. So where does y equal 0? So that means we have to set this guy equal to 0. So we say right here, we set this guy equal to 0. We say 0 equals x plus 7. We subtract 7 on both sides, and we get that x equals negative 7. So the ordered pair would be, this ordered pair would be negative 7. When x equals negative 7, y is 0. So that's going to be your x-intercept, where it crosses over. Final example, where does f of x equal 5? Well, we just set it equal to 5. This is finding the y value for that. So we set 5 equal to x minus 3 divided by x plus 4. You know, it might be better if I write it like so. Let's divide it like this. Easiest way to get rid of that is multiply both sides by x plus 4. I multiply both sides. Oops, lost track of the cursor sometimes. This guy will cancel with this. X plus 4, we distribute the 5 onto both of those. We get 5x plus 20, and this is just algebra at this point, equals x minus 3. Let's subtract the x on both sides. Oh boy, losing track of that cursor. That's going to be 4x plus 20 equals negative 3. Subtract the 20 over, you get 4x equals negative 23. Remember, when you subtract, subtract. And then finally, we'll just solve it by dividing by 4. So that means that when my x is negative 23 over 4, my y value, my f of x, which we were trying to solve for before because they gave us our f of x, equals 5. Altogether, that's what we're looking for. An ordered pair of negative 23 fourths, comma, y. So that's domain, that's intercepts, and those are values that we plug in to find either our f of x or find our f of some value.